All right. Number 41. This one looks really complicated. Obviously, you know, this is a more complex side over here, of course, but we're definitely going to want to start over here because we got something we can do. So left-hand side, sine of x plus y plus z. So basically, we're just going to have to do a repeated application of the angle sum formula. So let's group together these two. So the sine of x plus y plus z. This is sine, cosine, sine x plus y, cosine z, same sign, cosine x plus y, sine z. So now I need to use the angle sum for that, a little hard to see, sorry, and that. So it's going to be cosine of z times that quantity. So this is going to equal, so that's sine x cosine y plus cosine x sine y, all times the cosine of z, plus, then the cosine of x plus y is cosine cosine, and change the sign, sine sine, and if we distribute these into these binomials here, or two-term whatever, you get exactly this final answer. If you just look at it, it kind of matches up. So this times this, that's sine x cosine y cosine z, plus this times this, cosine x sine y cosine z, this times this, plus cosine x cosine y sine z, minus sine x sine y sine z. And I do think it's kind of interesting that this kind of has some symmetry to it. So basically these are all combinations of sines and two cosines and one sine. And it has, you know, and if you put them in x, y, z order, so it's the sine, cosine, cosine, the cosine, sine, cosine, and then the cosine, cosine, sine. So it's each combination of two cosines and one sine where you take the sine of x, y, and z, one in each, minus the sine of all three. So I don't know what any of that means, other than I'm done with my proof.